In this lesson we're going to look at spanning trees. But before we talk about spanning trees, we just want to talk about the generic tree. Now a tree can be as big or as small as what you make it. It is part of a bigger connected graph, but the only criteria is that it cannot contain any cycles, multiple edges or loops. So looking at this first one here, it is a tree. It's got quite a few vertices there, but it doesn't have any loops, cycles or multiple edges. Here's a bigger tree, again going through many vertices, no loops, multiple edges or cycles. This one down here cannot be a tree. You can already see a loop, a cycle, a multiple edge. So it has all three of them. So it is not considered to be a tree. Now here's a very important fact that you should remember. States that every connected graph contains at least one tree. So there must be at least one tree in a connected graph. And here, a tree with n vertices has n-1 edges. That might come in handy when we're doing some questions. In this example of a graph, you can see that there are two trees, the red one and the green one, but they are not the only two trees in that graph. If I started there, I could go there, there, there. As long as I don't create any multiple edges, loops or cycles, I can create a tree. So there's one. Here's another one. I could go from there to there to there. I could go along there. I could go up there. Again, make it as big or as small as I want. So a tree can be whatever size you make it. It just cannot contain these three things. So if a tree can be as big or as small as what you want, a spanning tree has to use all of the vertices. So it is a tree, can't have any multiple edges, cycles or loops, but it must use all of the vertices. So if you look at this example here, this red bit is your spanning tree. Now if you don't have it on your notes like that because yours are in black and white, make sure you highlight that spanning tree. Can you see that it has gone through every vertice there? And again, there are no loops, multiple edges or cycles. We also talked about the fact that if there were n vertices, there would be n-1 edges. Let's test it out for this. Let's count our vertices. So 1, 2, 3, 4, 5, 6, 7 and 8. We have 8 vertices. It should mean, therefore, that we have 7 edges. Let's see. 1, 2, 3, 4, 5, 6, 7. Yes, we do. Because remember, there is always one less edge than there are vertices in a spanning tree. In this example, we're asked to find 2 spanning trees. So remember, it's a spanning tree. We need to use all vertices. If it was just a tree, we wouldn't, but because it's spanning, we do. So let's think about it. There are many here, a lot more than 2. So I would probably go from E up to A, down to B, down to C, across to D, and I've used all my vertices there, and that is my spanning tree. That's one of them anyway. How about another one? Why don't I use, I'll start at E again. I don't have to, but I've just chosen to go across to B. Now remember, I don't want to have any loops or cycles. So I can go up to A from there. I could go down to C from there. And here I need to link in D, which I can from E. So you can see there I've used all my vertices. I haven't created any loops or multiple edges or cycles, so that is a spanning tree. There are many, many more. You have a go at drawing a couple. Obviously, there are many spanning trees in our graph. Now, if we had a weighted graph, we would be able to find the minimum spanning tree. And there should only really be one minimum spanning tree. It is the one with the minimum length. Fortunately for us, we do not have to do this one by trial and error. We can, in actual fact, use an algorithm, and it's called Prim's algorithm. So let's have a look at what that entails. So step 1 here says to choose a starting vertex, and it should be the one with the lowest weight. And if there are two of them, well, it just needs to be one of them. So if I was looking at my example down here, I would probably choose A as my starting point, because the lowest weight there on that one is 2. I probably could have chosen E as well. So there was a toss-up between those two, but A is going to be my starting point. Now that I've got my starting point, I need to now look at the next step, which then says work out which is the shortest edge to the next vertex. Well, obviously here you can see that we could go 2, 5 or 6, and 2 is obviously the shortest, so I would therefore go from A to B. So I start at A, look for the shortest, and I end up at B. All right, the next bit goes exactly the same way. I now, however, can look from A and B. So looking from A and B, again, this time I could either go these two or from B, 6 and 8, and the shortest one there is the 5 across to the D. So that's the one I'm going to choose. So I go down to D because it is the lowest one. This time, again, I'm going to do exactly the same thing and look from all 3 points. And of course, if I look from all 3 points, and keep in mind, I can never create a loop, a multiple edge, or a cycle. I always have to choose the option which doesn't give me that. So here, I'm going to go up to C, because that gives me the smallest route, the shortest length. So I'm going to go to C. And I'm repeating my process again. I'm looking from points A, B, C, and D. And my shortest length there is 5, which goes right through to E. And then again, this time I would inspect all my sides for the very last time. So I'm going to look from A, B, C, D, and E. And the shortest point there is to go from E to F, and that is 2. So my minimum spanning tree, therefore, would be all of those lengths added together. So it would be 2 plus 5 plus 3 plus 5 plus 2, which added up is equal to 17. So the diagram is my minimum spanning tree, and the actual length is 17. That is the smallest spanning tree that you can get from that graph.